Right. Hi, everyone. I know there are some questions revolving around beta oxidation, and so I just wanted to clear them up really quickly and hopefully give you guys a little walkthrough of the pathway. So first of all, beta oxidation, I like to think of it as in 4 steps. And so the first one is dehydrogenation. Next, we have hydration, and then dehydrogenation again. And finally, thiolysis. So first of all, dehydrogenation, another way to name this and talk about it is oxidation. So you will be losing electrons, and you will see we'll go from something that is a saturated carbon-carbon bond to unsaturated double bond carbon-carbon. And next we have hydration, that is adding a water molecule. We have dehydrogenation again, so that's oxidation, and then finally thiolysis, that is the breaking of the fatty acyl-CoA molecule into acyl-CoA and another fatty acyl-CoA, so it's the bond cleavage. All right, so the first thing you should know is that our fatty acids, they originally look something like this. So I'm only going to be drawing it as a 6-carbon chain, just for simplicity's sake. You obviously have to know longer chains, the C12 to 18 saturated, and the the 3 special cases of unsaturated fatty acids that Dr. Wu asked you to memorize. But for simplicity's sake, just because I'll be drawing it a bunch of times, I will be drawing only 6 carbons. And so we are starting off, and we have this fatty acid, and we know it's a fatty acid because we have a carboxyl group at the end. So this is a fatty acid. And we're going to convert this and activate it into our acyl-CoA molecule. So our fatty acyl-CoA molecule. So we'll have our coenzyme A right here, and we will have our 6-carbon chain as well. This activation requires 1 ATP molecule, so we'll see this later when I run through an energetic calculation. So it requires 1 ATP molecule, and then we are adding, as you can see, we're adding a coenzyme A to the reaction. All right, so let's actually talk about the beta oxidation now. So we're going to start off with our fatty acyl-CoA. And so we're right here, and we're going to do the first step. The first step is going to be our dehydrogenase step. So I'm going to abbreviate that as DH. Remember, it's also oxidation. And so we're going to start this, and what it is, it's going to produce this molecule. And what we are going to be adding is a double bond here. This addition of the double bond makes it from a saturated to unsaturated fatty acid just momentarily in the beta oxidation process. And we will be going from a reduced form to an oxidized form. So we are overall oxidizing the structure. And because we are oxidizing the structure, we will have to have an oxidizing agent that caused that. And that oxidizing agent is our FADH molecule, and that will become FAD plus, or just FAD normally. It will just become FAD, and that FAD needs, since it's an enzymatic process, it needs to be generated back to FADH. So it's going to go back to FADH, and that's going to be coupled to the reduction of Q to QH2. Doing this makes it so that we produce our QH2 molecule, which is one of the products from one round of beta oxidation. So we did our first step, and we have our dehydrogenation, we got our QH2, and we look like this right now. The next step is to go ahead, and we are going to do a hydration step. So we're going to use a hydratase, and we will be adding an H2O, and the H2O is going to add right here, and it will look like this now. And so we got rid of that double bond, but it's going to look like this. It's going to have an OH right there. And this is where we are right now. Our next step is going to be another dehydrogenation reaction. So another dehydrogenation. And since it is a dehydrogenation, it will be an oxidation. So we're going to need an oxidizing species. So we're going to use, this time, we're going to use NAD+, and that's going to go into NADH. And this will cause our substrate right here, it will now be oxidized. And so what it will look like now is this. So this is what we look like now. We have two ketones, and we are going to do now the final stage of this round of beta oxidation, which is our thiolysis. And we're essentially inserting in a CoA molecule, and it will come in and it will do a breakage of this bond. I just showed broken right here. And from that, we will get one acyl-CoA molecule. So it would be this portion of the fatty acid that now becomes our acyl-CoA molecule. And then this rest of the molecule will become a new fatty acyl-CoA. And this can continue going down beta oxidation until eventually it will all be just acyl-CoA. So it would first look like, it would end up, since we have 4 carbons left, after one more round of beta oxidation, we would have 2 more acyl-CoA molecules run from the start right here, and then these 2 carbons would also be in an acyl-CoA molecule. All right, perfect. So that's the general work through of beta oxidation for unsaturated, or for a saturated fatty acid, excuse me. But let's first talk about the energetic yield for it. So, and for this, I'm going to kind of go through one of the problems that was in the practice midterm. And so it dealt around mystric acid, which essentially, once it's activated, it would look like this. It is a 14 carbon long fatty acid. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so it's 14 carbons, and it's mystric acid. And so, first of all, I just want to help you visualize what beta oxidation is. By the different cleavages in the from each round of beta oxidation, you can say that they cleave, and I'll use red. They cleave this carbon right here. The carbon, it's groups of 2 carbons. So every round would cleave right there, then here, 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 here. And in total, I drew 1, 2, 3, 4, 5, 6. So mystric acid would go through 6 rounds of beta oxidation. This can also be summarized in a convenient formula that I like, and that is, if I remember it correctly, the number of rounds of beta oxidation equals the number of carbon atoms over 2 minus 1. And so for this case, we have 14 carbon atoms over 2 minus 1. So 14 over 2 is 7, minus 1 equals 6. So it'd be 6 rounds of beta oxidation, and that corresponds to what I just wrote earlier. So that's kind of just a visual understanding of why that formula works. Then we get to the ATP yield, and so the number of ATP molecules we will get from a saturated fatty acid equals 14. So you get 14 ATP molecules per round of beta oxidation. So you multiply that by the number of rounds. And then you also add 10 more ATP molecules. So that's a good equation you should know. And then also what Dr. Wu has said in lecture. So this is the formula that is present in the slides, but he said in the lecture, and it's shown in the practice exam keys, that you also subtract one more ATP because of the activation of your acyl-CoA earlier. So this activation step where you cost an ATP, that would lead to you subtracting one more ATP. Now, if I guess there is a caveat to this. So if he originally gave you mistric acid, which has an O- at the end right here, it first needs to be activated into the form with the fatty acyl-CoA molecule, and that would cause you to have to subtract -1 from it. But if he originally just gave you your mistric acid that is a fatty acyl-CoA molecule, so it had the coenzyme A on it already, then you would not include this -1. But for our purposes, let's pretend that it started off as just a fatty acid, and so we had to add this CoA molecule to it. So if we do an entire energy calculation, which is like he said in the practice exam, it would be 14 times the number of rounds. So we know the number of rounds is 6. So that's that. And then we're going to add 10. And then we're going to subtract 1 for the activation. And so we added a CoA-SH. Awesome. All right, so in total, 14 times 6 is, we got to do math really quickly, 84. Add 10, subtract 1, that would be 93 total ATP. Sweet. All right. Okay, so now that is just saturated fatty acids, but there is one last thing that Dr. Wu mentioned in lecture, and that revolves around when we're processing saturated fatty acids. So the fatty acids that you could be asked about that you would have to process that are saturated or that are unsaturated are these will be I'm blanking. There'll be cis double bonds. There'll be cis double bonds. And we know from up here that there are no cis double bonds in beta oxidation, right? There's no cis double bonds here. And so what essentially has to happen is we have to convert our cis double bonds into trans double bonds. And so we're going to start off and we're just going to use this linoleate is what is in lecture right now. So we're going to use linoleate. And so give me a quick second to draw it. It will enzyme A, and it is 18 carbons long. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, cool. So this is linoleate. And linoleate, it will go through beta oxidation. So like as we saw before, the cleavage will be at these sites, and so it's going to be good. Going right up to here, we're going to have, it's going to be just the same as it has been for our saturated fatty acids. But right when it hits this bond, I'm going to now draw it after these 3 rounds of beta oxidation. I'm just going to go down here. It's now going to look like this. It is going to go down, and then it has that. And then we go like that. All right, so we cannot go through beta oxidation when our fatty acid looks like this. So it has to go through a couple of steps. And so the first one is this enzyme. It's called acyl-CoA isomerase. And this acyl-CoA isomerase, it will isomerize this cis double bond, the first cis double bond. It will isomerize it into a trans double bond. And so from here, we're going to look like this. And I always got to count my carbons when I do this. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. Yes, we're all good. All right, so it will isomerize it into this farm. And if you if you notice, the form that this is in, if you specifically just kind of look at where I'm circling right here, it looks very similar to the stage after the first dehydrogenation step in beta oxidation. So it looks very similar to this molecule now. You have a trans double bond and some saturated regions after it. And so you are literally going to be inserting your unsaturated fatty acid into this stage of your beta oxidation. So from here, you are going to do you're going to go on, you're going to do your hydration, your second dehydrogenation, and then also your thiolysis. And so that one round, that's one round of beta oxidation, and you would end up getting a molecule like this. And it would cleave it would end up looking like this. So you just literally, you did one round of beta oxidation, you would end up cleaving at this bond, and you continue along. The important notice here, though, is that because you only did 3 rounds of beta oxidation, you did not do the first step. And that first step, if you remember, is the first dehydrogenation, and it's where you get a QH2. So since you did not do the first step, you will have no QH2 from that round. And this is why we subtract 1.5 ATP if you have one cis double bond. So if you just have a fatty acid that has one cis double bond, or if you have a fatty acid that has multiple cis double bonds, for the first cis double bond you encounter in your beta oxidation, you're going to subtract 1.5 ATP from the final yield, like what we calculated up here. You would subtract 1.5 ATP molecules. All right, then next, you continue on beta oxidation. And if you continue doing this, you first of all would you would do your dehydrogenation. So we continue, and this is the first dehydrogenation step, and you would get a molecule that now looks like this. I'm going to draw it here. I fear I've added a carbon or two, but if something looks weird, it may have been messed up, but overall the process I'm doing is correct. So anyway, once you do your first dehydrogenation right here, you would get this intermediate where you have these you would have the trans double bond right next to a cis double bond. And you also cannot do beta oxidation from here. So what we are going to do is we're going to do another enzymatic step. And what we're first going to be using is a reductase. So it will reduce your fatty acid. And it requires NADPH. so that NADPH will be converted into NADP+. You're going to get a molecule that looks like this. I'm really bad at counting these carbons, so forgive me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4, 5, 6. All right, cool. So you will end up getting this molecule, but if you would notice, this trans double bond is not in the location we need it to be, right? We need it to be over on this side, so that's where our that's a substrate of beta oxidation. That's where our next hydration step can happen. And so what we're going to do is we are going to run this through one more isomerase. And we're going to end up forming a molecule that looks like this. And so you will now have your trans double bond in the correct place. You can continue doing beta oxidation. And you will get your, you will end up degrading it all into acyl-CoA. All right, but however, I need to talk to you about the reductase step right here that converted this weird trans and cis double bond together into just one trans double bond. That did require an NADPH molecule, and we know that an NADPH molecule, it's basically synonymous to an NADH molecule, and so we're losing -1 NADH molecule from our energy source, and so that would be an equivalent of -2.5 ATP for doing this. So overall, when you have cis double bonds, the first one that is present, you will lose 1.5 ATP. So you count. So if we go back to our original, or I guess this is good enough. If we look at this drawing right here, for our first cis double bond, we would lose 1.5 ATP. And then for any subsequent double bond past that, if we had multiple cis double bonds in here, for any double bond past that, we would lose -2.5 ATP. So here total, we lost 4 ATP. All right, so one of the questions I've got has been why you don't also subtract another ATP or another 1.5 ATP from the subsequent double bonds. And so the important thing to just recognize from that is that when you go through this step where you have this weird intermediate right here, you end up you have already gone through the first step. You've already done the first dehydrogenation reaction. And so by doing that first dehydrogenation reaction, you gain the QH2. So you overall do not lose the ATP. You are doing all the necessary steps that give you the full energy yield for this step right here. But unfortunately, also, you are losing the 2.5 ATP from the reductase reaction that makes it so that you can metabolize this trans cis double bond monstrosity. Okay, so I would like to just quickly run through what the energy yield would be for linoleic acid, or linoleate, linoleate right here. And so it's the same exact thing. We're going to do the same exact thing as the ATP for our saturated fatty acid. And so we're going to do the same formula. So I'm going to just try to make them both in view right now. So, and I think I can actually move this down a little bit. So include that. Shrink it a bit. All right. So our energy yield. For linoleate. So So we're going to follow the same formula as up here, the 14 times the number of rounds plus 10 minus 1. We're going to do a little bit of change to that, but the first thing we have to do is to figure out the number of rounds of beta oxidation. That will be the same for unsaturated and saturated fatty acids. So it's the number of carbon atoms over 2 minus 1. So here, the number of rounds equals the number of carbon atoms over 2 minus 1. So that would be a total of 8 rounds of beta oxidation. And then now we move on to our formula. It is a little bit different now. So the number of ATP for unsaturated, it's the same as what we have up here. It is the 14 times the number of rounds. And we're going to add 10. And then we would subtract 1 if it started out as just a fatty acid and wasn't activated. But this is where it deviates a bit. So the first thing we do is for the first cis double bond, we subtract 1.5 ATP. And then we subtract 2.5 ATP for any other cis double bonds past that. I'm kind of running out of space here, but hopefully that makes sense. So for linoleate, since we had 8 rounds of fatty acid beta oxidation, we start off and we have 14 times 8 rounds. We're going to add 10. We'll assume that it started off as a fatty acid and then we added this CoA group. So we'll subtract 1 from that. Then we subtract 1.5 ATP because we did the first cis double bond. And then we'll subtract 2.5 ATP for the second double bond. This isn't a fatty acid, you have to know, but if you had, a third cis double bond in here and now it's a really long fatty acid, but you would subtract 2.5 ATP for the rest of these. But that's not something you need to know right now, or it's not relevant to this problem. So in total, the total yield for the linoleate in terms of ATP, 14 times 8 is 32 plus 80, so that's 112 plus 10 minus 1 minus 1.5 minus 2.5. So in total, the ATP yield would be 122, 121, 117 ATP for linoleate. All right, cool. So that's kind of just a rundown of how to solve these beta oxidation problems and the run through of the process of beta metabolism or beta oxidation metabolism. And so just generally, you have to know like the structures of these different steps. And I would definitely recommend, like which is a oxidation, hydration, or dehydrogenation and thiolysis. And you should know, the substrates, not the names of the substrates, just the structures of the substrates. You should know the like the cofactors, or I guess this isn't beta oxidation that I'm marking, but down here, this is beta oxidation. You should know the structures. You should know generally what the reaction does. You should know what the cofactors are. So these FAD molecules, QH2, water is inserted here. And then again, just know the structures of the different fatty acids in there. And then, be able to go through and do the energy calculations for both the saturated and unsaturated fatty acids. And then finally, for the unsaturated fatty acids, I don't think it's super important. It would be worth it to have it in your memory to know how these, how the conversion is done between the cis and trans, between the two cis bonds. Like it would be good if you knew this mechanism, but overall I think the biggest picture is knowing how you subtract 1.5 ATP for the first cis double bond and then 2.5 ATP for the second or any subsequent cis double bonds. And so yeah, I would, it's always worth it if you were able to draw out this mechanism and know it. There's a little gray area there. I don't know if he wants you to know this as well as just the saturated fatty acid metabolism, but overall, it's just good to know. But I hope this video helped a little bit, and good luck on your final. I'll see you around.